Alright, here's a quick overview of problems that seem to give the class difficulty. These are generally ones where more than half the students who answered got it wrong. Alright, block X of mass M slides along a horizontal surface when friction is negligible. Block X collides with block Y of mass 2M that is initially at rest, as shown in the figure. After the collision, both blocks slide together with speed Vs, as shown in figure 2. What is the kinetic energy of the two-block system before the collision? Well, that's a problem because we don't have energy before. We don't have anything about before. So I'm going to call this VI, the incoming speed. And I said that during a collision, we know that the momentum is going to be equal. So mvi is 3mvs, or vi is 3vs. And then the kinetic energy at the start is going to be a half times each mass times its speed squared. So a half times m times 3vs squared. And block 2 doesn't have any kinetic energy, so I'm not going to worry about it. So I have 1/2 m times 9vs squared, or 9/2 mvs squared. Block M of mass M slides across a horizontal surface when the friction is negligible. Block X collides with block Y of mass 2M that is initially at rest, as shown in figure 1. After the collision, both blocks slide together with speed Vs, as shown in figure 2. What is the speed of the center of mass of the two-block system immediately before the collision? So this obviously comes back down to what is center of mass, and center of mass is sort of the average position. And maybe the most important thing, and a worthwhile thing to keep in mind always, is that the momentum of the center of mass is the momentum of the system. And so we can just figure out, and therefore, so momentum of the system before, momentum of the system before is equal to the momentum of the system after. So let's say PCSI is PCSF, because during this collision no external forces act. And this is easy enough because this is then going to be 3m times Vs. So the momentum of the center of mass is 3m VCS. But of course, that's also going to be the mass of the system times the velocity of the center of mass. And we get something kind of goofy, but VCM equals VS. And you might find that a little strange, but what they're trying to bring home here is the point, which is the average of their two masses, the average location of stuff, is unaffected during the collision and always stays the same. By the way, almost certainly the S in V sub S is for system, because we often say that the system's velocity is the center of mass's velocity. All right, in an experiment, two objects, object X and object Y, travel towards each other and collide. Data are collected about each object before, during, and after the collision to create a graph that shows the momenta of object X and of object Y as a function of time. How should a student use the data found on the graph to verify the conservation of momentum? And this is one where they've got a lot of text, so you got to read the answers. So A, the sum of the magnitudes of the momenta should be compared because momentum is a scalar quantity. Well, momentum is not a scalar quantity, so this one's out. The vector sum of the momenta should be compared because momentum is a vector quantity. Well, that is certainly a true thing, that momentum is a vector quantity, so this is at least potentially in the running. Data from the graph cannot be used because the graph of the velocities of the objects of X and Y should have been created. That's kind of goofy, right? I mean, we're trying to conserve momentum, so a graph of momentum would be the right way to go. Data from the graph cannot be used because a graph of the force exerted on object X by Y as a function of time and a graph of the force exerted on Y by X as a function of time should have been created. And there's a couple of things. One, while the force as a function of time does get us change in momentum, by plotting both of these, we know those will be opposite and equal, and so this isn't going to be at either. So our only remaining answer was the original candidate, so we would go with that. All right. A student conducts an experiment to verify whether momentum is conserved for a situation in which a collision occurs. The two objects, object X and object Y, travel towards each other as shown in figure 1. After the collision, the two objects travel as shown in figure 2, which is, I think, together. Data collected from these three trials of the experiment are shown in the table. Which of the following statements is correct based on the data? And so, in one sense, you might want to say, well, let me just see if momentum is conserved. So let's take trial 1, where the momentum before is something like 2.1 kilograms times 2.1 meters per second plus 1.0 kilograms times minus 1.1 meters per second So we get something like 2.1 times 2.1 plus 1 times minus 1, or a momentum of 3.41 kilogram meter per second. And PF is going to be their sum, which is something like 3.2 kilograms, times their final speed, which is 1.1 meters per second, which is something like 3.52 kilogram meters per second. And the question is that close enough to within the thresholds of uncertainty? And this is actually a seriously annoying question. And if you found it so, good for you. Because really what you should be doing is saying, well, that was assuming I took the averages. But what if I had taken, for instance, the low velocities after? So what if I were to say that we're really 1 instead of 1.1 at the end? Then my final momentum would have been 3.2, which is below, right? So originally I'm too high. Now 3.2 would be too low. Is it consistent? Well, it means that the actual variation is somewhere, of this final one, is somewhere between 3.2 and 3.84. So there's a lot of variation in the final momentum. And in principle, we could apply that for all of these. But you can see that that's a vast number of calculations because there's, 16 things you have to apply out. The more formal way of doing this is to sort of, which is not required, but we know that P equals mv, so that means that the change in P is m times the change in V plus the change in m times V. This is basically something which would come out of calculus, which is why it's not technically on the AP1 roster. And then we can see that if we were to divide this by P, so we divide these by P, but really P is mv, then we get what's called propagation of error, which is that the fractional change in the momentum is equal to the fractional error in mass plus the fractional error in the velocities. So if we look here and we say that our fractional error in mass seems to be about 10%, and our fractional error in velocity seems to be about 10%, it means that our fractional error in momentum should be something like 20%. And 20% of 3.52, 20% of 3.52 is something like 0.7. So as long as we're within about 0.7, we're within our experimental error. And this tells us that we are well within that over here. But I honestly don't see a shorthand way from what the AP Physics College Board recommendations tell us we should be able to say here, except that it looks kind of close. And so since it looks kind of close, then we should take it. Honestly, if I were taking this test knowing only what they tell us we're supposed to know, I would probably have guessed, and I would not have spent any time on it. I'd read through and say, that looks about right, and I probably would have guessed A, but I might not have. The only thing I would say is it doesn't look like trial 3 seems to stand out, so I probably would have avoided that one. Like there's nothing in trial 3 that says, oh, this is wildly wrong compared to the others. But I do apologize. I actually have some feelers out there with other AP Physics teachers to see how the committee would really want people to have handled this, what was the context in which you're supposed to be able to do this. So it's not a thing you have to worry about for the upcoming test. For May, we'll figure out what we should do and make sure we address it before we get there. All right. A student must conduct an experiment in which an elastic collision occurs. In the experiment, block X of mass 2 kilograms travels with velocity Vx in the positive direction towards block Y of mass 2 kilograms at rest, as shown in the figure. After the collision, block Y travels in the positive direction with velocity Vy, while block X remains nearly at rest. Data collected of the initial and final velocities of each block for 3 trials of the experiment are shown in the table. Did the student conduct an experiment in which an elastic collision occurred, and is the system of block X and block Y open and or closed? So we really want to come back to and make sure we keep track of what this means. And of course what that means is kinetic energy is conserved. So our first thing is let's find the initial and final kinetic energies. which is, of course, irksome for the given that we have 3 trials. But all right. So trial 1. Let's get initial and final kinetic energies, which, remember, the kinetic energy is 1/2 the mass times the velocity squared. So for trial 1, the initial energy is the 2 kilograms times, well, honestly, and here we can just look at what happens to v squared to make our lives a little easier, because if v squared is the same, then the energy is the same. And yet what we have here, right, well, I guess we'll say, let's do that for real, 1/2 m1 v1 square plus 1/2 m2 v2 square, but we can factor out the half and have that as v1 square plus v2 square. So we have over here v1 squared and over here v1 square plus v2 square, the before and after. So 3.1 squared is 9.61, and 0.1 squared plus 2.4 squared is 5.77. And I'm not going to go any further and say the collision is not elastic. So that's out and that's out. And I'm not going to do the rest of them because that is so wildly off. And it will be wildly off for all of them. And then the next thing is, of course, is the system open or closed? And for that, we're going to have to go with, is momentum conserved or not? Because an open system would have forces from outside, whereas a closed system does not. And so we look here and we say, let's figure out the momentum before and after. But the momentum, again, is just P is mv, so we can just compare the velocities before and after because the masses are the same. So the velocity before is, let's take 3.1 and compare that to 0.1 and 2.4, which is 2.5. That's also not conserved, so P is not conserved, so it is this one. All right, block X of mass 2 kilograms travels across a horizontal surface towards block Y of unknown mass, initially at rest. Block X then collides elastically with blocks Y. A graph of the position as a function of time for block X is shown. Block X and block Y are made of the same material. Which of the following predictions about the motion of block Y immediately after the collision? So let's highlight some important things. Collides elastically, so KE is conserved. So the initial kinetic energy is X's plus Y's after. And then we have a position as a graph as a function of time. And we know that this means the slope equals the velocity. So what can I do? It means I can get the momentum of X before and after, and I can get the kinetic energy of X before and after. So let's take a look at these and start saying what we have here. The acceleration of block Y immediately after the collision is greater than the acceleration of block Y immediately before the collision. Well, I can actually throw that out without thinking anymore. Before and after these things, the acceleration is 0. There are only forces acting during the collision, so the acceleration is 0 before, and it's 0 after, so obviously they're equal, not one greater than the other. Part B, which is indicated here, is the right answer, so we'll come back. Kinetic energy of block Y immediately after the collision is greater than the kinetic energy of block X immediately after the collision. All right, well then let's find those energies. So beforehand, we have 1/2 times the 2 kilogram times the slope of this thing. We have 15 meters in 5 seconds is 3 meters per second, quantity squared. That's 9 joules. And then after, for X, we'd have 1/2 times 2 kilograms times, it looks like 5 meters in 5 seconds, or 1 meter per second. So that's 1 joule. This means that we have that 9 joules equals 1 joule plus the kinetic energy of block Y. The kinetic energy of block Y is 8 joules, which is certainly greater than that, so that's why that one's true. Let's look at the others. The magnitude of the change in momentum of block Y from immediately before the collision to immediately after the collision is more than the magnitude of the change in momentum of block X. But we actually know that, of course, well, actually we don't know that offhand, so let's put that on the back burner. The momentum of the system consisting of block X and Y immediately after the collision is less than the momentum before, but that can't be because it's a collision. We actually don't know enough to get the change in momentum for Y because we don't know what the value of the mass is. So that one's out as well. So as indicated, it would have to be B. An important thing about C and D is we don't know that they're wrong, but we can't prove that they're right. So they can't be the answer, especially when B, which is an answer we can show is right, is there. It outweighs the other two. A constant force Fa is applied to an object of mass m initially at rest. The object moves in the horizontal x direction. The force is applied in the same direction. After the force has been applied, the object has speed Vf. Which mathematical routines could be used to determine the time in which the force is applied to the object of mass m? Pick 2 answers. So we want delta t, and so we're going to go through, well, delta t is related to the impulse j, by saying that the impulse is the force times delta t. But we also know the impulse is delta p. So certainly one thing would be to just solve this and say, oh, delta t is delta p over the force. And that's answer A, so yay for that. Then we got to find the harder ones. But it's not that hard because we say we're initially at rest. So delta p, which is going to be mv final minus mv initial, is mv final minus 0. So delta p is mv final. So I go over here and I say this is mv final over fa. And look, that's answer B. So that's all that was. An object travels in the positive direction with a momentum of 5 kg/m per second. An applied force is exerted on the object, and a graph of the magnitude of the applied force as a function of time is shown. All frictional forces are considered to be negligible. Which of the following could represent the approximate momentum of the object after the force has been applied? Select 2 answers. All right, we want to find the final momentum, right? So we want P final. We know that delta P, of course, is P final minus P initial, and we have P initial, so that's good. P final is going to be P initial plus delta P. And then, of course, we're going to say, well, what is delta P? Delta P is J, which is the area on an FT graph. So we can say that the magnitude of J is the area of this blue region, which is 1/2 times 4 newtons times 1 second, or 2 Newton seconds. Now we need to be careful because this is the magnitude, right? It's the magnitude of the applied force, so this is the magnitude of J, which means it could be, in our thing, plus or minus. So we have that P final is P initial plus or minus the magnitude of J, because we don't know which way J is pointing. So it could be 5 plus 2, which is 7, or it could be 5 plus minus 2, which is 3. Oops, circle the wrong one though. So it should be these two, and it is. All right, B or D. And the key thing here again was that they gave us the magnitude of the applied force, so they're telling us only giving us absolute values, so we have to remember that it could be plus or minus when we're done. A variable applied force is exerted on a 2 kg block as it travels across a horizontal surface for a time of 2 seconds as shown in the graph. Before the force is applied on the block, it travels at a speed of 1 meter per second. The force is exerted on the block in the same direction as the block's displacement while the force is exerted. After the force is applied to the block, the force travels at a speed of 5 meters per second. Which of the following statements are correct regarding the motion of the block? Select 2 answers. All right, well, we have an applied force versus time graph. So one of the things I'd like to do is say, what is the impulse from that force, which is the area on an FT graph. So it's 1/2 times 5 newtons times 2 seconds, which is 5 newton seconds. So that might be useful to know. And then we could say, if we look at our answers here, we're saying the block travels a distance 4.5 meters. There certainly isn't anything here that says that, right? We just, because we don't know the acceleration's constant, so we can't use kinematics to figure it out. And we don't know any other, we have no other distance information. So I'm going to suggest A is probably not true. B is highlighted, so we'll come back. I'm going to skip that and come back to it. C, the change of momentum of the block from the applied force is 5 kilogram meters per second. Hey, I accidentally proved that one, so that one's true. The momentum of the system containing the block is conserved. Well, the original momentum was 2 times 1, and the final momentum is 2 times 5, or 10. That doesn't seem to be true, so I think we throw that one out. So we just need to verify B, that there's another force exerted on the block during the time which the applied force is exerted. How would we check that? Well, we could say if there weren't, then it should be that PF is PI plus J. So we would get 2 kilograms times 1 meters per second plus the 5 kilogram meters per second would be 7 kilogram meters per second. And then that would be the 2 kilograms times the final velocity, giving us a final velocity of 3.5 meters per second. But in fact, this is not equal to that. So there must have been some other source of impulse that I haven't included here, which means that this must be not be the only force acting. So there we go.